So good afternoon, everybody. Thanks for coming back to our session on spotlight presentations. So in this session, what we want to do is within the cluster of excellence, we have a number of projects internally in the cluster where a number of where typically two principal investigators jointly try to tackle a question at the intersection between machine learning and some other scientific discipline. And within these projects, we employed PhD students and postdocs. And now during this spotlight session and also during the other spotlight sessions, these projects are being introduced just for a short time. We have 5 minutes for the presentation, and if you wish, 5 minutes for questions. This also means that if you want to ask a question, you need to be really quick and enter it in the Ask a Question button right away, because once the presentation is over, I'm not going to wait for 10 minutes whether there are any more questions. So if you have one, please type it in pretty fast so I can see it. I hope everything else is now being set up so we can start. So the presentations are going to be one after the other. The first one is, in fact, by a PhD student in a joint project with Felix Wichmann and myself. David Künzle is talking about machine learning approaches for psychophysics with ordinal comparisons.
So, thank you for the introduction and welcome to my spotlight talk. So we start right away with my first slide where I introduce psychophysics. So measuring what's measurable in the world is the common goal of all natural sciences. Physics is maybe the shining example there. So in physics, people measure the light intensity or the sound pressure. In contrast, in psychophysics, researchers measure how we perceive this physical stimuli. For example, how we perceive the brightness of light or the loudness of sound. In psychophysical scaling, we ask questions like, how loud does this sound pressure feel? So this measured subjective perception as a function of the physical intensity is a so-called scaling function. Ordinal comparison is a relatively new approach in psychophysical scaling. I will show you in a quick example on the next slide. So this is a trial from ordinal comparison experiment about color perception. You can try it yourself. Is the color A more similar to B or to C? So to me, this red color is more similar to the violet than to the green one. In a real lab experiment, subjects judge hundreds and thousands of these triplets under lab conditions. And these hundreds and thousands of these judgments have to be aggregated to find this perceptual scaling function. Please go to the next slide. So if you think about color perception, the scaling function might look like the color wheel on the right. So in this color wheel, red is close to violet, but far from green. This means that we perceive red to be more similar to violet than to green. And if you think about it, this might be surprising because light is in color is just light at different wavelengths. But in wavelength, like you see in the spectrum on the left, red is close to green, but far from violet. And ordinal embedding algorithms help us to find such an scaling function like the one on the right, only based on these comparisons like you have seen in the slide before. Ordinal embedding is actually an active field of research in machine learning with sophisticated algorithms, but also several open questions. And in contrast to other approaches in scaling, ordinal embedding algorithms allow us to model even complex, non-monotonic and multidimensional perceptual scales. Next slide, please. So our project just started in the last months, but we tried to connect the research of machine learning and psychophysics. So on one hand, we have to identify the algorithms from ordinal embedding and the best practices from machine learning. But also there are some open questions like, how can we measure goodness of fit or uncertainty in terms of ordinal embeddings? And on the other hand, we have to bring all these as methods and software to the field of psychophysics. So we have to communicate our methods in a common language with the practitioners in the field. We have to go into the lab and do experiments ourselves. And because these experiments sometimes take hours and hours, we think that we can make them more efficient by clever sampling of the trials. And maybe most important, we also have to think which new opportunities we have with these new methods. So are there actually which scaling functions which are non-monotonic or multidimensional? You could ask yourself, what do you think? How many dimensions do you actually perceive a human face? So overall, we think that ordinal embedding might lead to a paradigm shift in perceptual scaling research. And it may allow us to ask completely new questions. Thank you. Next slide, please. So this was my spotlight, and now I'm open for your questions.
Thank you very much, David. We received one question so far in the question chat, and it's by Konstantin Jenin. So the question is whether the psychophysical measurement scale, ordinal ratio, learned from the data, whether the measurement scale is learned from the data or whether it's assumed ex ante. So I think ex ante probably means that you need to know it in beforehand. I don't know Latin. So Konstantin, you need to bear with all the machine learners out there.
So the perceptual scale is an interval scale. The one which you want to model is an interval scale. But the subjects do these ordinal comparisons which are ordinal on an ordinal scale, but because you have two ordinal comparisons, you can estimate an interval scale out of this.
Okay, thank you very much. I don't see any further questions. So then my suggestion is that we simply move on to the next project. Thanks to David, and the tech team needs to bring in the next person. Thank you.
Thank you.
Hello.
Hello.
Now I think our next speaker is on stage as well. So the next speaker is Hassan Shah Mohammadi, who is working in the project Enhancing Machine Learning of Lexical Semantics with Visual Mining. And this is a project that is jointly conducted between the groups of Hendrik Lensch and Harald Bayen. So welcome, and you're ready to start now.
Thank you for the nice introduction. So as she said, I'm Hassan. I work with Dr. Hendrik Lensch and Harald Bayen, and the topic of our project is Enhancing Machine Learning of Lexical Semantics with Visual Mining. So in the next slide, I'm gonna briefly say what that is. So many of you have already heard of text embedding models such as word2vec, where the goal is to map a word into a numerical vector in a meaningful way. And many of these models work by leveraging from the statistical information in a corpus, usually the co-occurrence information of other words. However, that raises a problem of if we compute the meaning of a word based on the meaning of other words, then what is actually meaning, which is called symbol grounding problem. And the reason is our knowledge of word is linked with our perceptual and motor system. For example, action denoting words such as kick or lick involves the activation of the area of our brain controlling those movements. Moreover, as it turns out, people are much faster recognizing if this picture is a pumpkin if it's in original color versus if it's in gray or another color. And that indicates that the perception that we have for the word is linked with our perceptual information that we gain through our life. And so the goal of this project is to kind of combine textual and visual information to overcome this limitation. In the next slide, you will see our first approach to tackle this problem, which is a visual grounding model. So the goal here is to take as an input an off-the-shelf embedding, in this case glove embeddings, which is purely trained on text. And we trained a grounder matrix to map this embedding into the grounded space, in which the visual information is also combined. And we train this grounder matrix by means of two tasks. The first one is the image captioning task, where you can see on the way right, we're trying to generate the next word based on the image. And the second task is a binary classification one. So at the beginning, we have a sentence. We map it into the so-called textual space using the glob embeddings. Then we use our grounder matrix to map it into the grounded space in which the feature vector of the image is also combined using a GRU encoder. And the output of GRU is mapped into the textual space again by using the transpose weight of the grounder matrix. And then we again use a transpose weight of the original embedding to get the index of the next word. The second task, however, it tries to tell to predict if this given sentence describes the image or not. So we have them combined in the same strategy. However, the output is a binary classification problem. We train these two losses to update the grounder matrix, and we can, by use of grounder matrix, we can get our grounded embeddings. So in the next slide, you will see we evaluated our grounded embedding on the word similarity task, where the task is to predict how similar a pair of words are based on human judgment. For example, smart and intelligence are similar, however, old and new are not. And the metric here is Pearson correlation. So the data set that we use is nicely categorized into adjective, nouns, and verbs. And more importantly, it is categorized into 4 sections based on the degree of concreteness or abstractness of that a pair of words. We also compare our model by a model called Picture Book, which is a model by Google Brain, published 2 years ago. Here on the first row, you see the performance of Glove, and then Picture Book plus Glove, and at the last, you see the performance of grounded embedding. As you can see, our grounded embedding alone outperforms Glove, and also Picture Book plus Glove with a high gap, and moreover, it can generalize much better in a way that if you look at the highly abstract work, you see the performance of Picture Book is very low, it's 14%. However, the performance of our model can actually outperform Glove on this. The same story is true for adjectives as well. And no matter if the word is abstract or concrete, we still have this nice improvement over the word. In the next slide, you will see our second approach to tackle this problem, where we have a video captioning model. So basically, we extract the feature of each frame in the same scenario. However, we would like to employ a spatiotemporal attention on each frame, so we can later on combine this visual information with the word embedding, and we use a 2-layer RNN to generate the video caption. However, this work is at the beginning stage, so we don't have the result yet, but we would like to focus on a spatiotemporal attention for feature transform and a visually grounded embedding in the word embedding section. In the future, next slide. In the future, we would like to improve other word embeddings as well, such as BERT or Word2Vec. Moreover, we would like to move on to the transformer architecture, where we have the privilege of looking at all the word at the same time, not only from one direction. And we like to, as I said, explore the effect of grounded embeddings for video captioning, and finally promote the video captioning model by adding other modalities such as audio. Thank you, and feel free to ask a question if you have.
Thank you very much for your presentation. So I can see one question currently, which is by Philip Behrens, and he asks, do you have an idea why highly abstract words benefit from visually grounded embeddings?
Obviously, there is no obvious clue, but what we're trying to do in our model is that while training, we didn't update the original Glove embeddings, which means that we use the same function to get our output, and that means that the sort of the abstract information that is already there is preserved. So we might push them in the right direction to be further improved. Yeah.
Mm-hmm. Okay, thanks a lot. Are there any more questions? If yes, you would need to type them right now.
Yeah.
Okay, one more. In fact, 2 more. Okay, I start with the first one. Are there ideas to relate the joint embeddings to event cognition or causal reasoning?
I'm not familiar with what event cognition or causal reasoning is. I don't work in that area, to be honest.
Okay, I think this is also a difficult question to ask in the beginning of a project. So I would say what you're currently doing is sort of the first steps, and then one can still see further how to relate it to other areas of machine learning. The other question is whether you integrate spatial temporal analysis.
That second part, actually, my colleague works on that. However, we would like to, so we have a bunch of frame, right? And we would like to add this information in each frame to a specific word. So if you use a spatial attention, it means that in each frame, for example, if you're looking for a word cat, we might get the information in that specific of the image and add it to the word. And in a temporal dimension, we might recognize that the cat is actually walking. So we recognize the verb and add it to the word embeddings. That's the story of what we're going to do. However, we haven't done that yet. Yeah.
Okay. Maybe also for our audience, all of these projects have essentially been started, or many of them have just started like a couple of months ago. So in many projects, we are still at the stage of doing the first steps.
Great.
Okay, thank you very much. I think if there are no questions anymore, then we're going to move on to the next speaker. So the tech team needs to swap speakers now. Thanks a lot.
Great.
Hello. Seems like our next speaker is on stage. Welcome. So the next presentation is given by Matthias Karbauer, who talks about causal inference with a spatio-temporal generative mode. You see this contains many of the keywords that we have already seen in the previous presentation or in the questions. This is in a joint project by Martin Butz, Hendrik Lenz, and Thomas Scholten. Yes, Matthias, you're ready to go.
Okay, thank you for introducing and having me here. The general project goal is, in principle, to produce weather forecasts, that is, to predict the complex, partially chaotic dynamics of weather by means of a data-driven approach, like a recurrent neural network. But today, what I would like to show you is, well, as we've been introduced, the causal inference of effects on a spatio-temporal data set, which I would like to show you on the next slide. Yeah, the spatio-temporal process I'm talking about is the so-called circular two-dimensional wave, which we implemented such that waves propagate from a point source outwards throughout the field. They are reflected at the borders and they are modified locally by obstacles in the water. We can think of them as being like stones lying in the water and blocking and affecting the propagation of the wave. The obstacles differ in quality, how strong they affect the wave, meaning that darker obstacles have a stronger blocking effect on the wave. The general goal now in this task was to set up a model that is capable of predicting the wave dynamics far into the future, and simultaneously inferring the obstacle positions and their effects on the dynamics of the waves. So the model did never receive any real information about where the obstacles are positioned and what their effect is on the wave, but the model was only presented with the pure wave dynamics through the space, developing over time, and well, had to infer the obstacle positions in order to properly predict the unfolding wave dynamics. Good, the inference, next slide, please. The inference of the obstacles or of the static map referring to the obstacles is visualized here, and you see in the early training stage, the top left figure, that the model at the beginning had roughly no idea about the different effects of the different obstacle types, but it already had some raw idea about where obstacles are positioned and where not. Impressively, until the end of the training, as you see in the center figure at the top, the model was very accurately producing a static context map, so to say, of the obstacles, and not only concerning their positions, but also their friction coefficients, if you want to say so, so their effects on the wave, and it almost directly hit the ground truth at finding the positions and their effects on the wave. It was inverted, nevertheless, it directly referred to the ground truth. And the evolution of the static context, basically, of the obstacle positions and their friction coefficients, you see at the bottom plot again. Each line corresponds to a particular object type, meaning how strong its blocking effect is on the wave. And in the beginning, so at the left of that plot, all obstacle types were roughly the same. And throughout the training, seeing more training examples and more iterations, the model increasingly well did differentiate the different obstacle types until at the end, it clearly separated each obstacle type and even inferred obstacles that have never been encountered during training properly into the linear mapping. So the dashed lines are obstacle types that have never been encountered during training. Good. Next slide, please. What is all this now useful for? As I said in the beginning, we are heading at producing weather forecasts, and as you might know, weather is a particular complex process and is modified by several parameters that we might not even know of. And with the procedure that I just introduced, we hope to incorporate parameters that we are not aware of, but which pretty much might have an effect of the unfolding of temperature, for example. And we applied this procedure on a rather coarse data set, and you see at the left center plot the final latent variable coding that the model produced, which partially encoded east and west information, as you can see, but also, and that was quite impressive, sea and land information, although the model has never ever seen ground information like soil types or a land sea mass or something like this. But this latent code emerged just by observing the temperature and having to predict and unroll the temperature into the future properly. And yeah, at the bottom you still see the prediction of our model at the left side, and on the right side the ground truth. And you can say, well, it's not perfect so far, but we are on a good way, I would say, and we are pretty much looking forward at making more progress in this project, and finally coming to very precise weather forecasts. Thank you.
Thank you very much. I don't see a question right now, which is in the indication box. I might want to start with myself. So in the previous example where you talked about these objects that you wanted to recognize, what kind of knowledge about the physical model did you feed into the algorithm? Was there any kind of knowledge, or how did this really work?
Well, the inductive bias, the grounding model that we used to approximate the process is already structured in a grid structure, or in a grid way. So we had, speaking simply, maybe we have a graph neural network which has processing nodes at each grid position, and then getting information from each neighboring grid cell. And from this setup of the model, we already have this grid structure, but the model had now to develop a function at these grid nodes which reflects the unfolding of the dynamics. So the only inductive bias that we provided was the grid structure of the process. Yet we did not provide any information about where obstacles might be positioned and what kind of effect they have on the unfolding dynamics.
Sorry, my microphone was switched off. Don't worry. So there's a second question, which is whether there's a physical interpretation of the latent variable, for example, in terms of the climate observable or other temperatures.
Yeah, that's quite interesting to determine an explanation of the latent variables that are emerging. We are collaborating with Meteorological Institute at Stuttgart-Hohenheim, and we've asked them whether in the numerous latent codes that emerged throughout the project or throughout the training, what codes these might be in terms of real physical terms or phenomena. And we heard that there's some albedo mask emerging apparently, which corresponds to the north and south mapping or to the reflectance of the surface. So in fact, there appears to be some realistic physical explanation that can emerge in the latent state.
Mm-hmm. Okay, thank you.
Thank you very much.
Just trying to see whether there's I mean, there are some more difficult questions about whether you have already reached out to our research group leader, Bedata, which I think was a bit difficult because he had been locked away in a different country due to Corona. And I don't see any other questions right now. So my suggestion is that we thank you for your presentation, and we're going to switch to our last speaker in the Spotlight session. Thank you very much. Okay, hello everybody back. For the last presentation, we have two speakers sitting or standing there, namely Thomas Gläsle and Kerstin Rau. Both of them work in a joint project by Thomas Scholten and Philipp Hennig about interpretable spatial machine learning for environmental modeling. So it's up to you.
Yeah, thanks for that. And let's directly go to the next slide and see what this is about. So our project is concerned with developing and adapting methods for digital soil mapping. And this means modeling the value of a soil attribute, such as carbon or clay content, over an area of interest. Since it is costly to obtain and analyze soil samples, we often have only a limited number of direct measurements of the target quantity. And these can be far apart and unevenly spaced, as you can see in the plot on the left. For this reason, it is common to incorporate additional information via other covariates that are available at higher resolution. Apart from predicting the value of the target quantity itself, we are also interested in keeping track of the uncertainty that the model has about the prediction and in an understanding of why certain predictions were made and how to incorporate domain knowledge into the model. Let's go to the next slide. Currently, we are working on building physics-informed models that are based on Gaussian processes. Our first approach is to build models based on custom topographic covariance functions that capture geographically relevant aspects of the underlying mechanisms. This can, for example, be based on non-Euclidean distances induced by water flow properties, rivers, or more generally other topographic aspects like the one shown on the right. The idea behind this is to add similarity information between distant locations that exceeds their pure geographical closeness relationship. Our second approach is to extend the Gaussian process models by imposing geographically motivated relationships in the form of linear partial differential equations. On a technical level, this works by adding virtual data points that act as measurements of these equations. This now allows encoding statements like the target attribute increases in the direction of more vegetation or something like that. And this can be useful to incorporate prior geoscientific knowledge into the model and also to develop and test new hypotheses by checking their usefulness to predict the output quantity. And yeah, with this, I give to Kerstin.
Yeah, on the next slide, you can see such a description of a geography-dependent variable. We want to describe a global geographical model that informs the regression process. So we do this through partial differential equations derived from geographical knowledge that relate temporal and spatial changes in several interrelated geographical processes. These kind of processes, for example, here for soil thickness, you can see on the in the first equation. So there's are different processes like upbuilding, for example, chemical weathering. So when in the soil is existing chemical weathering, then the parent rock transforms into new soil, and of course then the soil thickness can increase. There are other upbuilding processes like deposition of soil material that could be fluvial or aeolian. There's also a negative term that represents the removal processes like erosion or leaching of dissolved components. We have to consider that these processes are also affected by other factors like climate or topography, and as you can see in the second equation. So if there's a higher temperature, the chemical weathering is normally faster and we have more activity in the biotic part in the soil. So the soil thickness can increase again. Or if there's growing more vegetation, then we have more potential initial soil material. Our goal is to describe these individual parts which influence the soil thickness or other variables. And with this combination of these different linear partial differential equations, we want to model our soil property. The important point here is that the PDE does not need to be an exact description of a geographical model, because we don't want to build a simulation. We want to define a physics-inspired regression model. And the connection to the reality will come through the included observed data. So thanks for your attention, and we are open for your questions.
Thank you very much. Again, I'd like to ask the audience to enter a question. And in the meantime, I'm going to ask one myself. So you said in the beginning that you're going to use Gaussian processes and that you need to model the covariance function of the Gaussian process depending on sort of the, I mean, in my words, the landscape of the piece of soil that you're currently looking at. So can you also track the uncertainty about this covariance function? Because my feeling would be that it's really difficult to come up with a meaningful covariance function based on such a complicated thing.
I'm not sure how to track the uncertainty of the covariance function itself. Well, no, I don't know.
So essentially the uncertainty that you're going to track comes from the data itself or from the posterior distribution? Well,
okay, we build a covariance function, and that is composed of different parts. There's one part that can come from the uncertainty of the data itself, and then also we have an additive term that relates the covariance between points on distant locations. And this additive part is scaled by some hyperparameter which can be fitted through the data. And the hope is that we can somehow detect the relevance of these parts automatically through the data that is provided.
Okay, so there's yet another question about the covariance function, namely how do you use how in practice would this work if you have experts who can sort of help you designing this covariance function? So what would be the process, like in which way would you build this covariance function with the help of external experts?
Okay, let's say in a very simple scenario, there's an expert that says what is really important for the estimation of the clay content is the elevation of this point, right? And then one could simply map the x-y point coordinate through the digital elevation model, obtain the elevation at that location, and use that as a distance measure into the covariance function. That could be a very simple approach.
Okay, thanks a lot. So currently I don't see any other question. So my suggestion would be that we simply close the Spotlight session. First of all, I'd like to thank Thomas and Kerstin again. And then we have yet another break. We will meet each other back at 5 p.m. Our time, Central European time, for the presentation of Jakob Macke, which is going to be the final presentation of this conference day today, and then there's going to come more tomorrow. So hopefully see all of you back at 5 p.m. Thanks a lot.